So far, so good. Except that what I just showed you won't work. And let me show you why. So in the real world, so here I have this little function, okay? And so this is f of x, right? And it's got some stuff, and then it takes a jump, and it's got some more stuff over there. So that's intensity is a function of x. If I actually take the gradient of that function by just doing, say, a right difference, right? What I'll do, I'll apply my derivative operator, and I'll get this. And one might ask, where is the edge? Well, we can see here the edge is really, whoops, I missed. The edge is right there, but in this mess, it's sort of hard to tell. And the problem, of course, is that we've added noise, and that noise has caused us to have positive and negative derivatives all over the place. So let's look a little bit more about the effect of noise on some of our derivatives and what we might do about them, okay? So here we have, again, more of that striped duck. And here we have the gradient image. And what you can start to see is as I add noise to the image, my gradient starts to fall apart. That is, I'm starting to see this. I had this little bit of Gaussian noise, and now I'm turning into these big salt and pepper noise, which feels like salt and pepper noise. Just these large spikes are happening within my derivative. So we have to handle that noise somehow. You probably know how to handle. How do we handle noise? We filter, we smooth, we get rid of it, right? We did that before? Come on, you paying attention? All right, so here's my image, F. So now let me apply a smoothing kernel, H. Okay, so I'm just going to smooth it. So when I smooth it, I get, this is H convolved, doesn't matter whether you do convolution or correlation. H convolved with F, and you see now I get a nice smooth function. So now that we've smoothed the signal, we can take the derivative, and what you see is we get this nice smooth peak. So where is the edge? The edge is going to be at this peak right here, corresponding to that edge right there. So basically, in order to find our edges, we're going to have to basically apply smooth gradients somehow and look for some peaks. Before we go ahead and do that, remember this whole notion of associate property and linearity, etc.? We can save ourselves an operation because the derivative of H convolved with F is the same as the derivative of H convolved with F. So what does that look like when we're doing this edge detection? It's the following. So here we have the same F that we had before. Now I take my H and I take the derivative. That now looks like this. When I apply that function directly to F, I get out the same value that I got out last time, which has to be because of the associative property of linear operators and derivatives and filtering being these linear operators. That also saves us an operation because we can just take this filter and apply it and no more derivatives have to be done. All right, so last question, okay? So we have these nice peaks. We have to find the peaks. We have to find the maximum of that derivative. How do we find maxima? We take more derivatives. So we're going to have to take another derivative. So now, instead of just doing a single derivative, we're going to take a second derivative. So before H was just a Gaussian, this was our first derivative of a Gaussian. If we take the derivative of that again, we get this, what's sometimes called inverted Mexican hat. And you'll see that when we do it in 2D, right? Because it's kind of like this sombrero shape, but up and down, right? When we apply that operator to the image, we get this nice zero crossing with this strong slope. And that's what corresponds to our edge. All right, and this idea of a strong slope, zero crossing, we don't have to find general maxima. We just have to find any place where the value is zero and that nearby has a strong gradient.